Hey, this is Warner. We're going to take a look at Chapter 2, Part 2 notes. This one's a little bit more about force, and the person who really helped us understand force was Isaac Newton. He was probably the greatest physical genius ever, and he came up with three laws of motion. So we talk about those three laws of motion, the first, second, and third law, and we'll go into those in more detail. He also invented calculus, and even though we're not a calculus-based course, a lot of what we know comes from the applications of calculus to physics. He published his laws in 1687, and it's in the book called The Mathematical Principles of Natural Philosophy. So what is force? Force is really just a push or pull. We've kind of talked about that a little bit. And these forces can cause an object to accelerate. So when you push on the accelerator in your car, you start moving very quickly because you're accelerating. Accelerations can also be negative. So when you hit the brakes, you slow down. That's also an acceleration that we call a deceleration. So we can speed up or we can slow down. And then the last way that we accelerate is we change direction. So if you have somebody running towards you and you push them to the side a little bit, they change direction. Newton's first law is also called the law of inertia, and it basically just says, and you've heard this before, a body in motion stays in motion at a constant velocity, and a body at rest stays at rest unless you have some sort of external force that acts on that thing. It's usually applied to the horizontal component of velocity, which is assumed not to change during the flight of a projectile. Um, so the first law is counterintuitive. So even today, people still believe that a force is required to keep an object moving. That's just not true. Aristotle did believe that there was a force that needed to keep things moving, but later on, Newton kind of proved him wrong. And as a Physics 150 student, you're going to know better by the time we're done. So here's a good example of what happens. Let's say that we have a ball on a hill with a height of h1, and that ball rolls down the hill, and then when it rolls up the other side of the hill, because there is a force now, there is something working against it, which is this little incline here, that ball will stop on the other side. It doesn't matter if I take the hill and make it less steep, and then it will still stop at that same height. So these are some of the things that Newton decided to kind of do and see how they worked. He also noticed that if you start a ball at that height and then you don't have some sort of force acting against it, it will just continue to roll. And so that's where that first law of motion comes from. A free body diagram is something that we will sketch for objects, and that represents every force acting on an object. It will not include any forces that act on other objects, just on the objects we look at. So for example, let's say that you had a regular physics book instead of the digital edition. If you place that book on the table, there are two forces acting on that, and those two forces cancel each other out, but they are both still there. It's kind of like if I push on you and you push on me at the same time, we're both pushing on each other, but the net force or the force overall is zero. The force that pulls down, we're going to call that the force due to gravity. Okay, gravity is an acceleration, so we want to be really careful that we always call this the force due to gravity, and we usually abbreviate it F with a G down on the bottom. You would not want to abbreviate it with a capital G, and we don't want to abbreviate it with just a little g, because this is an acceleration, and then this, you're going to find out later, is actually a number. It's a constant. Um, the force pulling it down is the force of gravity. If that was the only force acting on it, it would fall right through the table. But there is another force that holds that book up, and we call this force the normal force. And we can either say F with an N, or we can just give it an N. Either one of those is absolutely fine. So that's called the normal force, and we'll look at it a little bit more here in a second. The forces on the book are balanced, and so therefore the book just kind of sits there and doesn't move up or down. Here's another example that shows no net force. Gravity is pulling you down, and the floor is pushing up on you. So we say that those forces are balanced, and there is no net force. So you just kind of stand there. For an object in equilibrium, we say that all of the forces are equal to zero. So that means that all the forces in the x direction and all the forces in the y direction are zero. And you might even have a z direction. So we've got y, which would be straight up. We have x, which would be straight to the right or left. Y could also be down. And then we have another vector that points out towards us, and we call that z. So this is that three-dimensional picture. Typically, we'll just do things in two-dimension. We're just going to look at the y and the x component. Adding that third one makes it a lot more difficult. So here's a good example. It says a red-tailed hawk that weighs 8 newtons is gliding due north at a constant speed. The key here is constant speed. If it has a constant speed, then we know that there is no net force. No net force. They want to know what's the total force acting on the hawk due to the air. Draw a free body diagram for the hawk. So since the hawk is gliding at constant velocity, it is in equilibrium. And the net, so be careful, there are two forces acting on the bird, but the net force is equal to 0. So let's go through and identify those forces that are acting on this hawk. So here's the picture of the hawk. We have the force due to gravity, so there's that Fg that we talked about before. And that one's pulling the hawk down, but because the hawk is traveling at a constant speed and maintaining its altitude, we also have the force of the air pushing up on the hawk. And so you'll see this one as F air. Both of these vectors are equal but opposite in direction, so the overall force is 0. So when I add the force of gravity and the force of air, I should get a sum of 0. So that would be my net force acting on the hawk. The forces on an airplane in flight heading eastward are as follows. So what we'll do is we're going to draw a really cheap, inexpensive airplane. There we go. And gravity is pulling it in this direction. Let's actually switch colors here. So we know gravity is pulling it straight down towards the Earth. That's the force due to gravity. We have another force acting kind of straight up, and that would be the force of the air. We have a force that is pushing it forward, and so this one we're going to call the force due to the thrust. And then we have one more force that tries to keep the airplane from moving forward, and that would be the force of drag. So we're just going to put FD. So all of these are forces acting on the plane, and it says what is the net force on the plane. So we're going to take all of these numbers and we're going to kind of look at what's going on and see if we can figure out what the net force is. To do this, we need to have all our components. So notice that we have up is y, down is negative y, east is in the positive x, and west is in the negative x. So if we have our airplane, we've gone ahead and put all of our labels on. Notice that sometimes we're going to use W for weight. That's the same thing as using Fg. Lift here is L. We said that was the force of air, so that's the same thing. We tried to use Ft for thrust. They've just used T. And then we said Fd is the force due to drag. It doesn't matter how you label them as long as they kind of make sense. Just be very careful with weight that you don't call it big G or little g, because that would be bad. Let's look at all the forces in the y direction. So we're going to say the sum of the forces in the y direction, and we're always going to do the first one, which is positive. So this would be F of air. They call it L. And then the one that's pointing in the negative direction is the force due to gravity. So we're going to say that's minus Fg. Earlier, they told us that we have 16 kilonewtons or 16,000 newtons. So we'll just do 16 kilonewtons for the force of air lifting the plane. And we're going to now subtract from that the weight of the airplane, and that is also 16,000 newtons. So here we see that the sum of the forces in the up and down direction, okay, so in the y direction, are 0. That means that this plane is flying level. It is not gaining altitude and it is not falling. So it is flying level and there's no acceleration in the up or the down. We also need to take a look at all of the forces in the x direction. And so when we do the forces in the x direction, we're just going to say some of the forces in the x direction are equal to, let's pick the one going to the positive first. We said that that's the force of thrust, and then we can subtract from that or just add to it the negative force, which would be the force of drag. So I've used my notation Ft and FD, and if you want to use the capital T and the capital D with the arrows over the top, that's fine too. So at this point, we've got the force of thrust, which is 1.8 kilonewtons, and we're going to subtract from that the 0.8 kilonewtons from the drag. Now, obviously, we want the thrust to be bigger than the drag, because if not, we won't have a force propelling that airplane and accelerating in the forward direction. And so if you subtract the two, we end up with 1.0 kilonewtons, and that would be to the east, since it is moving in that direction. And that is example 2.7. Let's go ahead and move to the next one. This is example 2.8. So to slide a chest that weighs 750 newtons across the floor at a constant velocity. So notice that means that there is the sum of the forces, or we can call this the net force, will be equal to 0. So it's at a constant velocity. We push it horizontally with a force of 450 newtons. They want us to find the contact force that the floor exerts on the chest. So because this chest is moving with a constant velocity to the right, it's in equilibrium. The net force has got to be 0. We need to go through and look at all the forces on the chest. We're going to draw a free body diagram, and then we just need to make sure we remember the forces in both the x and the y direction are equal to 0, the sum of the forces. So the first thing we do here is let's just think about the forces acting on that chest. We are pushing it to the right with a force that we're going to call F. Then we have another force that is pointing straight down, and that would be the weight of the chest. And then the chest has two components really of force, and we're going to call that a contact force. And that contact force is moving both to the left, and it is also pushing in the up direction. So there's two contact forces. One of those contact forces is the normal force. That's the force that keeps it from falling down through the floor. And the other one is the force of friction. We're going to talk about the force of friction here in a second. But let's go ahead and solve this one for both the forces in the x and for the forces in the y. So the sum of the forces in the x direction would be equal to the force of our push. So I can even put FP here if that makes it easier. And we're going to subtract from that the force of friction. And that's our contact force. We know that the sum of the forces here need to be equal to 0. We know the force of the push is 450 newtons. And then from that, we're going to subtract off the force of friction. So if I go ahead and solve this for the force of friction, notice I'm going to add force of friction to both sides. And so here the force of friction is also 450 newtons. And that makes sense because we said that it is traveling at a constant velocity. And because it has a constant velocity, that means that the sum of the forces in the x direction need to be equal to 0. For the y direction, we're going to do the same thing. We know that the sum of the forces in the y direction should be equal to the normal force, which is pushing up, minus the weight or the force due to gravity. So remember, we also call this one the force due to gravity. The normal force here, we don't really know what it is, but we do know its weight. And so here we know the sum of the forces is equal to 0. We know that the normal force, we're not sure what that is, but we do know the weight, and we said that the weight here is 750 newtons. If this is 750 newtons, I want to find out what that normal force is. I'm going to just take the 750, I'm going to add 750 to both sides, and I find out now that that normal force is equal to 750 newtons, and that is in the up direction. That is in the up direction. And that is the end of example 2.8. Newton's third law. Oh, you know what? Yeah, Newton's third law. So Newton's third law basically says that for every action, there's an equal and opposite reaction. And we call these interaction pairs, and each force has an interaction partner. So if F exerts if A exerts a force of F on B, then B will exert a force of negative F on A. And so at this point, we need to define a system. A system is all the particles that make up a certain thing. So we could think about a soccer ball. And if I have a soccer ball, all the particles that make up that soccer ball are a system. We can classify all the interactions that affect the system as either internal or external. And so for the internal interaction, both the interacting objects are part of the system. When we add up all the forces on the system, we get what we call the net force. And that is every internal interaction contributes two forces, an interaction pair, and those two things should add up to 0. Gravitational force is one of those forces that is an action-reaction pair. And according to Newton's law of gravitation, we have two objects that are exerting forces on each other, and they are the same. You're going to find out very quickly that I can only push on something as hard as that thing pushes back. If I push on a small box that's empty, I can push it pretty hard. At least I think I can. But in reality, I'm not pushing hard at all because it doesn't push hard back. If I use my body and try to push a car, on the other hand, I have to exert a lot of force because that car can push back very hard. So there's an equation that we're going to use anytime we want to find out what the force due to gravity is on an object, and that's this equation here. So the force due to gravity is equal to, this is a constant, it is a very small number. So you'll notice it's 6.674 times 10 negative 11th. We call that the universal gravitational constant. And it has a unit of a Newton times a meter squared over a kilogram squared. That's just like having maybe a meter per second. It's just that this one has a lot more to it. And so I also need to have two masses. If I'm looking at the force between the moon and the earth, m1 might be the earth and m2 might be the mass of the moon, and then r is just the distance between the two. So it's like a radius. If you think about it, if I start here and then go all the way out to the moon, that would be my distance r. And that is what we call the Newton's law of universal gravitation. We'll do some problems that deal with that. So here is our first problem that we're going to look at. And this one basically just says when you're in a commercial airliner cruising an altitude of 6.4 kilometers, by what percentage has your weight as well as the weight of the airplane changed compared to your weight on the ground? So to do this one, they've given us this really nice diagram here, and you'll see that we are our distance from the center of the Earth. But that includes two things. That's the radius of the Earth, and then it's also the altitude at which we're flying at. So to find the distance, r, we need to add the radius of the Earth plus the height that we're flying at. So that's the first part that's a little bit more challenging for what we're doing. So R2 here is really just the radius of the Earth plus that height. And then that will be what we use in this spot. So let's go ahead and take a look at the next step here. And in the next step, this one's already kind of worked out for us. We're going to look at the proportion of the two weights. So this is weight 2 divided by weight 1. So here we've got big G times the mass of the Earth times the mass of our moon divided by the radius squared. And then we're going to do the same thing. And then this R1, remember, was the radius of the just the Earth itself. So we're looking at these two radii as we go through. So R1 is just the radius of the Earth, and R2 would be to the airplane. I think I said moon earlier, so we really want to make sure that's the airplane. So this is the radius to the airplane, and this is just the radius of the Earth. We find out because we have the mass of the airplane and the mass of the Earth are the same, and G is the same, all those cross off, and now we just have a proportion that shows the relationship between the radius of, and notice that this is R1, so this comes up here, the R2 then comes back down on the bottom, R1 over R2, and they're both squared. We said R1 was the radius of the Earth squared, and then R2 is actually the radius of the Earth plus the height at which that airplane is flying. Now we can do those two, and we end up with 0.998. So since 0.998 is equal to 1 minus 0.002, and 0.002 is 0.2 divided by 100, your weight would decrease by only about 0.2%. So not a really big change in your weight. The gravitational field strength, so for an object near the Earth's surface, the distance between the Earth and the center is pretty equal to the radius of the Earth. So you don't have to get real technical with this one. If I go through and rearrange my W equation here, so weight is equal to big G times the mass of the Earth times the mass of you divided by the distance between you and the Earth squared. We're going to factor out the m here, and then what we'll do is we're going to just kind of look at that gravitational strength G. So gravity is equal to big G times the mass of the Earth all over the radius of the Earth. Now you're asking what happened to the little m. So let me show you what happened to the little m. W here is really equal to m times G. And so when I set mg equal to this equation right here, when I set it equal to this equation, so here we've rearranged so we can just kind of ignore this part. When I set these two things equal to each other, notice that your mass cancels out and it doesn't matter. Now we're left with gravity is equal to the universal gravitational constant times the mass of the larger thing divided by its radius. And for looking at on Earth, we know that we have gravity has a value of about 9.8 newtons per kilogram. So it's approximately equal to 9.8. Depends on where you are on the Earth and your altitude. But for the most part, we're going to use 9.8. Sometimes it's even easier just to use 10 because of calculations. So that's pretty easy to do. So that takes us to the next part. So here's the problem with weight. They want to know, are weight and mass the same thing? And they are not. Weight is defined as the force due to gravity. So we have said that when we write the force due to gravity, we write it Fg. We can also write it W, but we're also going to write it mass times gravity. And so mass is a component of weight, but weight is not a component of mass. Mass kind of stands on its own. Mass will not change. It does not matter where you go unless you lose or gain a body part. So for example, if you get a haircut, you're going to lose some mass. But if you don't do that and you go from here to the moon, your mass would stay the same. Your weight, though, would change. Your weight would change itself. So there's our equation. Weight is equal to mass times gravity. And the relationship between mass and weight in vector form is just weight is a vector because it has a direction, and so does gravity. Mass does not. Mass is a scalar. And so your mass is never negative, but your weight can be negative because it points down. The average value of gravity near the Earth's surface, as we said before, is about 9.8 newtons per kilogram. So here's a good example. It says in most countries of the United States, we sell things in grams or kilograms rather than in force units, which are pounds or newtons. The scale will still measure force, but it's calibrated to show the mass of the produce instead of its weight, which is a little bit different. So we want to know what is the weight of 350 grams of fresh figs in newtons and in pounds. So fig newton, I think that was kind of on purpose when they did that. Basically here weight is just mass times the gravitational field strength. So we're going to assume that the gravitational field strength is 9.8 newtons per kilogram, and the weight in newtons can be converted into pounds just by using this conversion factor of 0.2248 pounds for every newton. If I want to know what the weight is, I'm just going to multiply my mass times that gravitational field strength, and I end up with about 3.43 newtons. Now I need to convert that from newtons to pounds, and it would be 3.43 newtons times 0.2248 pounds per newton, and that gives us now 0.771 pounds. So here we know that the figs weigh somewhere around 3.4 newtons or 0.77 pounds. In the next video, in video 3, we're going to start looking at contact forces.